Hey everybody, can you guys see me and see my slides and hear me okay? Thank you. Sorry I'm a little late getting in here. There was somebody in my regular and reserved classroom, so I had to do a little scramble to find an alternative space, but hopefully nobody will come busting on into the classroom that I'm in now during our class, so we'll just see how it goes. All right, so let me grab my laser pointer. Okay, so before we jump right into the chapter 9 alkynes that we've been talking about this week, just a couple of reminders. You guys do have exam 3 coming up next week. I've listed it here as Monday 4/25. That is because we will not meet for class on Monday 4/25. But just like with your other 2 exams, there will be a window for you guys to take the exam, and I will post that for sure in your slides on Friday, but also via an announcement in Canvas. I'm not sure when I'm going to open the window, but the window will remain open until 11:59 p.m. on Tuesday. So you will have Monday from at least 1 o'clock. At least 1 o'clock. I may open it earlier. I haven't decided yet. But beginning Monday at 1 o'clock and then until Tuesday at 11:59 will for sure be the window, and I might widen the window a little bit wider depending on a couple of different conflicts and scheduling snafus that I have. So I'll be clear about that on Friday, what the window actually is, but it will definitely open no later than 1 o'clock on Monday, and it will definitely close no later than 11:59 p.m. on Tuesday. The next thing I want to mention is that you guys can still upload your chapter 8 charts for partial extra credit in case you missed the upload deadline of Monday for full extra credit points. That spot in Canvas is just open, so anytime you get around to uploading a chapter 8 chart, you can do that. And the next thing that I want to talk to you guys before we get into alkynes is just a little moment to reflect, because Friday is Earth Day, and as you can see by this little cartoon that I pulled from the internet, it says make every day Earth Day, and that's something I subscribe to. In honor of Earth Day on Friday, I'm going to give you guys an opportunity to earn a little bit of extra credit if you so choose. So chemists don't just celebrate Earth Day. Chemists formally celebrate Earth Week this whole week. And the American Chemical Society, or ACS, hosts all sorts of webinars, especially this week, about environmental issues. And so what I've done here is given you a link to a sort of a conglomeration list of their free webinars. And if you want to earn some extra credit, this is totally optional, but if you want to earn a little bit of extra credit, you can watch one of these webinars if you choose one that is about environmental issues according to Earth Day, and write a short summary about it that you submit into Canvas. And again, the ACS stands for American Chemical Society. This is a professional society for chemists at all stages of their careers. So they have a lot of professional development opportunities for students, for faculty, for industry workers, for retired people. They host conferences. They have a lot of really cool benefits of being a member of the society. And I'll answer y'all's questions in a minute, but I want to mention that some chemists celebrate Earth Day all year long. And so what I'm going to do is keep this offer open until the end of the semester. So I know this is a busy time in the semester for everybody. There are a lot of webinars that are being hosted this week, but there are also some hosted in May. There are some that have already passed. And so this offer is going to be open for you guys until literally the end of the semester. And I'll be creating a spot in Canvas where you can do this upload, and it'll have more clarity about what I mean by the end of the semester and the actual deadline and additional instructions. The other thing I want to mention is that these webinars, if you go to this link and you see a webinar that interests you, but the timing doesn't work out for you to attend that webinar live, if you still register for that webinar, a lot of times if you register, they'll send you a link to be able to view it offline after the fact. So pick a webinar that interests you, like this is your chance to kind of explore the opportunities that are out there. You can watch more than one webinar. You can only get extra credit for watching one, but you can watch as many of these as you want to. They're free webinars, and there are some really interesting topics there that are all relevant to Earth Day or environmental issues. So Samantha, I think you had your hand raised first. So go ahead, Samantha, with your question.
I just wanted to know if it was clear which ones are about environmental issues, to make sure we don't, accidentally submit one that's not about environmental issues.
Okay, great question. Most of them are going to be fairly obvious. If you think it's obvious, you can just go forward with it. I'll put a couple of suggested ones up when I post this in Canvas that will be safe. If you have any concerns, you can send me an email and say, hey, I was thinking about watching this one. What do you think? And I'll let you know, yeah, that applies, or no, it does not. Okay, other questions in the chat box. I will probably release Quiz 6 scores before the end of the day today, probably. I am teaching Chem 302 next semester. As far as I'm aware, that class is full right now, but they may open up more seats just before the semester begins. And we do have one more quiz. I talked about this a bit on Monday. After exam 3, the rest of that week we'll be spending talking about chapter 10, which is about the synthesis of alcohols. And there will be a quiz on chapter 10, but it is going to be an open book, take home, do it on your own time kind of a format. So it will not be a quiz during a class period because we just don't have enough class period time. And also if I make it open book for you guys, that's a chance for you guys to boost your grades. So I'll talk more about the quiz on chapter 10 when we get to chapter 10, but that answers that question. And you're welcome, you're welcome, you're welcome. And any other questions, now's the time. And if not, we'll jump into alkyne chemistry. Ready, go. Both the synthesis and reactions of alkynes are covered in this chapter. And on Monday, we covered basically an introduction to alkynes, which actually was entirely a review. Every single thing I talked about on Monday, you have seen before at some point during the semester already. So today we're going to move on and we're going to jump in starting with the synthesis of alkynes, which just like many of these other kind of features here, mirrors alkenes. So I want everyone to take a moment just on your own, and you can put your answer in the chat box or shout it out. But if I'm telling you the synthesis of alkynes mirrors the synthesis of alkenes, think for yourself about what do you know already about how to synthesize an alkene? So we saw in chapter 7, we had a whole chapter called structure and synthesis of alkenes. So think back to chapter 7, and what do you know already about how to synthesize alkenes? How do we know how to do this? Right, yes, thank you. Elimination reactions. Perfect. In chapter 7, the only 2 reactions we learned in chapter 7 are actually just 2 mechanisms of the same reaction, and that is an elimination reaction. We learned about E1 and E2, doing an elimination of HX, right, an alkyl halide to get an alkene. And indeed, the alkynes are going to feel so familiar. So here we go. If you think about what you want to do to create an alkyne, if you remember, an alkyne is a triple bond, which is a sigma bond and 2 pi bonds. So if we need to make 2 pi bonds, and we can generate 1 pi bond by eliminating HX, then we need 2 halides, 2 atoms of a halogen in our molecule to be able to do 2 sequential eliminations to get an alkyne. So what that means is that our starting material, instead of just being a regular alkyl halide, has to be a dihalide, right? Because we have to do this elimination twice to get our 2 pi bonds that make up our the 2 pi bonds of our triple bond. And the halogens have to be in the right place. They have to be either vicinal, which means on the carbons next to each other, or geminal, which means on the same carbon, like the word Gemini, which is twins. So we're going to do this elimination. Another name for doing an elimination of HX that we learned in chapter 7 is dehydrohalogenation, right? So dehydrohalogenation means we're going to remove a hydrogen and remove a halogen. Dehydrohalogenation of a geminal or a vicinal dihalide. The first one will give a vinyl halide, and then in the second step, we'll do a second dehydrohalogenation to get an alkyne. So here's what this looks like. As I mentioned, a vicinal dihalide is when your halogens are on the carbons next to each other, and a geminal dihalide is when your halogens are on the same carbon. In the first reaction, this is exactly the reaction that you guys already know from chapter 7. We're going to use a strong base to eliminate HX from this molecule. And our end result in this case is going to be our new alkene that we just made, just like we were making alkenes in chapter 7, except one of the carbons will also have a halogen as a substituent, which makes this a vinyl halide. That vinyl means that the halogen is attached directly to a carbon participating in a double bond. From this vinyl halide, if we have a strong enough base, we can do it again. We can do another elimination because we still have a second halogen that's a leaving group, and there's a proton on the carbon next door that can be removed. So we can still do this deprotonation reaction, this elimination reaction where we deprotonate this proton and have this halogen as a leaving group, as a halide. That'll give us our second pi bond, or our end result of our triple bond. If we have a geminal dihalide where both of our halogens are on the same carbon, the same thing happens. We can undergo elimination under the same types of conditions that you've seen for chapter 7, where we eliminate HX across of this molecule to generate an alkene. And again, we'll have the same vinyl halide. It's actually an identical vinyl halide to what we have above. So mechanistically, we're using strongly basic conditions. We have to use strongly basic conditions because the second elimination is not easy to do. It's a difficult reaction and it's slow. So we have to choose an incredibly strong base to be able to do this in kind of harsh conditions. Now, when we do this, because we're using strong base, this is going to be an E2 elimination. And so in both cases, you're going to do your elimination reaction in a concerted way. So we're not allowing for any carbocation intermediates in this case because we've chosen a strong base, and we had to choose a strong base because the second elimination reaction is not easy to do. Okay, so I want to take this slide to talk about some subtle regiochemistry considerations here. And I'll come back to this idea of subtlety at the end. So as you can imagine, the location of that triple bond is going to depend entirely on where the halogen atoms were in the original molecule. But there are situations where more than one product is possible. So first I'm going to show you a situation that's pretty straightforward. If you do an elimination on this 2,3-dibromopentane, our strong base that we're going to use is potassium hydroxide. It's called fused potassium hydroxide, and we're going to use a high heat conditions. And when we do this, we're going to get elimination first of one molecule of HBr across these two carbons, and then the other one, generating our alkyne between the two carbons that had the halogens present. So when we do this KOH elimination, or this potassium hydroxide elimination, this is how we're going to get the most stable and most highly substituted alkyne. These conditions favor the thermodynamic product, or the most stable product here. And it's also dictated by where these bromines are within the original molecule. However, you can imagine situations where if we had both of these bromines on this carbon, our triple bond could have ended up here, or it could have ended up here, right? And so if we use KOH, like I've shown here, that favors the internal alkyne, or the most stable alkyne. There's a second set of reagents that we can use called sodium amide. Also, we're going to still apply heat. The sodium amide is a stronger base, an even stronger base, and in a second step, we'll need to add water, which I'll mention in a minute, that would favor a terminal alkyne. And the reason that this green process down below favors a terminal alkyne is because the sodium amide base is strong enough to deprotonate the end product. And so I'll show you what I mean by that in a second. First, here's the reaction that would happen with KOH. So this time the substrate we're looking at is a dichloropentane, where both of our chlorine atoms are on the fourth carbon in the chain. Well, it's actually the second carbon in the chain if I name it properly from the right to the left here. But both of our chlorines, this is a geminal dichloropentane. And so that means that we could either deprotonate 2 protons from the left, which are shown in pink here, to get an internal alkyne, or we could deprotonate 2 protons from the green side, from the right side. That would give us a terminal alkyne. And so if we use alcoholic KOH or molten KOH, if we use potassium hydroxide under these harsh conditions, we will favor deprotonating the internal protons to get an internal alkyne here. If, however, we use sodium amide, the opposite will occur, and we will favor deprotonation of the green protons. First one, which would put an alkene that's a terminal alkene, and then the other, which would create our terminal alkyne. And the reason that this sodium amide reaction works in this way is because when you get to this step, we've now generated an acidic proton, like I talked about on Monday. These terminal alkynes are acidic enough to be deprotonated by sodium amide. And that is indeed what happens. The sodium amide deprotonates this terminal alkyne again to give you this carbanion. And that's why you would need to follow by water in a second step to put that H atom back on here, to quench this anion and put that H atom back on here. But overall, the sodium amide allows us to create a terminal alkyne, even though the internal alkyne is more thermodynamically stable. This is a stronger base, so it's going to be able to deprotonate more quickly. And so it'll grab the protons that are easiest to grab, which are the sterically less hindered ones on the end. And it drives the reaction all the way in this direction because it also can deprotonate this terminal alkyne to force everything to go into this direction. This last step is a very thermodynamically favorable process. Okay, so I want to come back to this idea of subtlety. I'm presenting this to you guys because it's in your book and I want to be thorough, but if you guys can remember that either KOH or sodium amide are good for creating triple bonds out of dihalides that are either vicinal or geminal, I'm not going to split hairs about this because I know you guys have a lot to remember. So just kind of don't worry about the subtleties here, but for those of you who are on board with everything and want to understand why there's this distinction because it's drawn out in your book, I wanted to be sure to take a moment to explain it. But this is indeed a subtlety. Okay. That covers us for the synthesis of alkynes. That's it. It is just the double elimination of dihalides that are positioned appropriately. Any questions about the synthesis of alkynes before I move on to the reactions of alkynes? Yeah? Okay, great. All right. What I want to focus on now is the reactions of acetylides, and we'll talk over the next couple of slides about what I mean by acetylides. I introduced this idea on Monday, but I'll talk more in more detail about it over the next couple of slides. And this next section is really most of the new chemistry of the chapter. Everything else after this section is going to be some variation on something you've seen before. The same way what we just talked about with the elimination reactions is essentially a variation on something you've seen before. So for these acetylide reactions, that's actually also stringing together concepts you guys have seen before. And I think you'll understand what I mean by that in a little bit. All right, before we get into that, I want to remind everybody from Monday and also from chapter 4, we've talked about the acidity of hydrocarbons and how sp3 and sp2 hybridized hydrocarbons are very difficult to deprotonate. They have huge pKa's, and so these are not considered acidic hydrocarbons at all. However, As you keep increasing the S character of your hybrid orbitals and you get down to an alkyne, which has an sp hybridized orbital, then when you deprotonate this CH bond and create this carbanion, the lone pair of that carbanion is held more closely to the nucleus because of the more S character of that hybrid orbital. And because you can hold those 2 electrons in that lone pair of that carbanion more closely to the nucleus, they will be more stabilized. And as we all remember from chapter 4, if you can stabilize your conjugate base, then that makes your acid more acidic. And you can indeed see that in the pKa trends. So the CH of a terminal alkyne is around 25. And so that definitely makes it more acidic than sp2 or sp3 hybridized hydrocarbons. But it also makes it acidic enough to be deprotonated by sodium amide, which is the same reagent we were just talking about on the last slide. Ammonia has a pKa of 36, which means if you have deprotonated ammonia, which is called sodium amide, that deprotonated ammonia is a strong enough base to deprotonate a terminal alkyne, which has a pKa of 25. So I'll talk about that over the next couple of slides in more detail. So this is exactly what I just said on the last slide while we were looking at the chart, that terminal alkynes are more acidic because of the higher S character in those hybridized orbitals, and that we can deprotonate these terminal alkynes using a base like sodium amide. Note that hydroxide or alkoxide bases are not strong enough to deprotonate the alkyne. And you can see that if I flip back to this chart, the pKa of an alcohol, which is one of the ones that I asked you guys to remember as a benchmark, is around 16. And so that pKa of that alcohol is lower than the pKa of the terminal alkyne, which means that the alkoxide base is not going to be a strong enough base to deprotonate the alkyne. Okay, here's what this looks like in an actual example. Here we have cyclohexyl acetylene. So we're using the common naming term here where we describe this molecule by using what the substitution is of acetylene. So cyclohexyl acetylene is a terminal alkyne, which means that it has a pKa for the CH bond here of about 25, which means that if we expose it to deprotonated ammonia, such as sodium amide, that sodium amide is a strong enough base to deprotonate that cyclohexyl acetylene because the pKa of ammonia is 36. And so this reaction is favorable in the direction that I'm showing you here. And therefore we can generate what's called sodium cyclohexyl acetylide. And this term, acetylide, refers to deprotonated version of a terminal alkyne. So a carbanion where that lone pair is on that triple bond carbon. Now I want to take a moment and draw out a sort of a strange, weird aspect of organic chemistry. This base is called sodium amide, and I just want to pause and take a moment because this word, amide or amide, either way you say it is fine. That word is the same word used to describe functional group amide, which we learned about in chapter 2, that has a C double bond O and that carbon additionally attached through a single bond to a nitrogen. Those amides, the functional group of amide, is completely different and completely unrelated to this sodium amide or the amide anion that we're talking about here. It is the same word applied to 2 completely separate scenarios and 2 completely separate situations. So try not to be confused. I'm sorry that that's what they named sodium amide, but that is what they named sodium amide. So sodium amide is going to come up a lot in this chapter because it's very useful for deprotonating terminal alkynes, as we have seen. All right, so here is another example. Here is butyne or 1-butyne, and this is also a terminal alkyne, which means it also has a pKa of around 25, which means that it can also be deprotonated by sodium amide. And I'm just showing you also the electrostatic potential maps up here. So basically the take-home point here is that sodium amide, which we can draw like this or we can write like this is the base that is strong enough to deprotonate any terminal alkyne. So it doesn't matter what's going on over here on the other side of the triple bond. If you have a CH bond on your triple bond, you can deprotonate that with sodium amide. What you can't do is deprotonate an internal alkyne with sodium amide, right? Because if you look at this compound, this is but2 ion as opposed to but1 ion, there are no CH bonds in this molecule that are sp hybridized, right? This is not a terminal alkyne, it is an internal alkyne. And so there are no CH bonds that are sp hybridized, which means all of the CH bonds in this molecule have a higher pKa than that of a terminal acetylene, and actually a higher pKa than that of ammonia, and you will not get a reaction. So it must be a terminal alkyne to be deprotonated. So in the chat box, there's a question that says, what specifically makes sodium amide special compared to other strong bases when it comes to deprotonating terminal alkynes? So I'm going to scooch back a couple of slides here to answer that question and take us back to this chart. So sodium amide is a strong enough base because the conjugate acid of sodium amide is ammonia, and the pKa of ammonia is 36. So because the pKa of ammonia is 36, then that ammonia, NH bond of ammonia, is going to be less acidic than the CH bond of a terminal alkyne, which means that if these two anions were fighting over one proton, that one proton would go to be with what would then become ammonia, the amide to become ammonia. If the CH bond in question were being compared to an OH bond, the pKa of the CH is 25-ish and the OH is 16-ish. That means that the CH bond is more acidic than the OH bond, which means that if these two conjugate bases were fighting over just one proton, that proton would go to the alkyne. So that means that this alkoxide here is not a strong enough base to deprotonate this terminal alkyne. And this goes back to the concepts that we learned in chapter, I think it was chapter 2, or it might have been chapter 4, but about acids and bases. It's chapter 2, I think. Okay. Moving on here, now that we know how to deprotonate terminal alkynes with sodium amide, we can do stuff with them. Before I do that, I just want to mention, your book talks about this, so I wanted to mention it here. This is the reaction for how you generate sodium amide. Some people also call it sodamide when they combine sodium and amide. I am not going to ask you to memorize this equation. I'm never going to use the word sodamide. This part is all you need to know, this second reaction here, that if you have sodium amide and you expose it to a terminal alkyne, you will make the acetylide. And again, this term acetylide refers to the carbanion where the carbon is part of a triple bond. And that's what we're talking about here, is a series of reactions of acetylides. Once we've made this acetylide ion, that anion is a strong nucleophile. So it can go and do other reactions. It can do addition reactions and substitution reactions. And that's actually the point of this section, is the reactions that this acetylide can do. But first we had to know how to make that acetylide. So what can we do with something that's a strong nucleophile? Well, we can do an SN2 reaction. So this is going to be one of the main pathways that acetylide ions react, is with SN2 reactions. And this is one of the best ways to synthesize substituted alkynes. If we take a terminal alkyne and electrophile, such as methyl iodide, then an SN2 reaction can occur, and we can substitute what used to be a terminal alkyne. Well, this is now a deprotonated terminal alkyne, but you can imagine easily how this used to be a terminal alkyne. So we can take a terminal alkyne and we can turn it into an internal alkyne. So a couple of things to note here. This is a reaction of alkynes because we're taking a terminal alkyne to do this reaction. But check it out, the product is a substituted alkyne. So this actually is considered also a synthesis reaction for alkynes. You can synthesize a new alkyne from a terminal alkyne. So it falls under both synthesis and reactions. Another couple of notes that are very important. As you might imagine, this only works with terminal alkynes as the substrates. And that is because you have to generate this acetylide. This is a reaction of acetylides, a deprotonated carbanionic form of a triple bond. And so if you had an internal alkyne, you would not be able to do that deprotonation. Also, I should mention that, of course, we know from chapter 6 that SN2 reactions work best with less sterically hindered reagents. And so if we want to take an acetylide ion and react it with a primary alkyl halide, we can actually create a longer chain substituent on our alkyne. And this is special for acetylides now, what I'm about to say. Of course, it's not special that the less hindered your substrate, the better an SN2 is. But these methyl halides and primary alkyl halides are the only substrates that work for this reaction. And the reason for that is because the pi bonds of the acetylide are actually pretty big electron clouds, right? So it might look like this molecule is not very sterically hindered because it only has atoms in a linear way, but there are big electron clouds on both sides, on kind of all sides of this triple bond, because remember we have 2 pi bonds, which means we've got overlapping p orbitals in the plane of the page and perpendicular to the plane of the page. And so the acetylide ion is actually somewhat sterically hindered as a nucleophile. So it's only going to work with a methyl halide and a primary halide. But if you use a primary halide, it's a really useful reaction because you can attach, instead of a methyl group, some long, and it could even be branched out here somewhere as long as it's a primary alkyl halide at the site of attachment. Okay, so what happens if you have secondary alkyl halides? Well, if acetylide ions are strongly nucleophilic, we have to assess whether or not they're strongly basic also. And it turns out the answer to that is a resounding yes, because acetylide ions, if we think back to the chart, the pKa chart I was showing you, acetylide ions are going to be more basic than a hydroxide ion. So they are strongly basic. And that means that if you show an acetylide ion, an alkyl halide that is not a primary or a methyl halide, then instead of substitution, because of the sterics involved at the electrophilic site, you will get an E2 elimination. So if you have a strong base, like an acetylide ion that favors E2 elimination, so if you have the conditions for it, you would end up getting, indeed, in this case with isopropyl bromide, which is the secondary alkyl halide, you would get an E2 elimination where you would essentially just protonate or acetylide, returning it back to the terminal alkyne that it was, and you eliminate HBr out of your alkyl halide to generate propene and a Br minus leaving group. So keep that in mind, that it has to be a methyl halide or a primary halide to do the SN2 reaction. And then if you have anything more than that, you'll follow an E2 elimination process. Okay, let's try it out. Let's do this with a practice problem. So this is not going to be turned in. This is just for us to do together, but I do want everybody to try to do it. So here's the problem. Show how to synthesize 3-decyne from acetylene and any necessary alkyl halides. Well, what's the very first thing we need to do? The very, very first thing we need to do is make sure we know where we're headed. So I want everybody to take a moment and draw 3-decyne out for yourself on your piece of paper. If you're using a line angle drawing, make sure that you're very careful to get the right number of carbons. I would encourage you, after you draw it, to go in and number the carbons and make sure you actually have 10 for decyne. Okay, so hopefully your decyne looks like this or something like it, or the line angle version of it. And I just want to point out, let's double check and make sure we do have 10 carbons. We've got 1 here plus 5 here, so that makes 6, 7, 8, 9, 10. And we have our triple bond in the right position because we have to count from the side closest to it. So we've got 1, 2, 3. So we have dec 3-ine here. And you could have drawn it the reverse way. You could have drawn it in a line angle format. There's a lot of different ways to draw it. So what we need to do is go from acetylene, which again is the most simple triple bond, HC triple bond CH, to decyne. So everybody take a moment to think about how you would do that given what you know. If you look at acetylene, this is actually a terminal alkyne on both ends. So we can generate the acetylide ion sequentially on each end, and we can react each end with an electrophile. So then what we need to do is look at our target molecule and think about what the electrophile we would need would be to put in each side. So if I look over here at decyne on the right-hand side, I want to be able to add a 2-carbon unit, right? And so I know I need to have a primary halide or a methyl halide, but a methyl halide is only a 1-carbon unit. So if I need a 2-carbon unit that's an alkyl halide, I can use ethyl bromide on this side. Over here on the left-hand side of the molecule, the way I have it drawn, we're going to need to add 1 plus 5, so 6 total carbons. So we will need a hexyl bromide or a hexyl halide of some sort. So let's put this all together. We have to do this sequentially and stepwise to make sure that our anion is fully formed and we're putting in one side of the molecule at a time. So here's what this looks like. We can take our acetylene, and if we focus on the left-hand side first, we expose it to sodium amide to create the acetylide anion, and then we expose it to this 6-carbon electrophile. This is N-hexyl bromide, and that will install the N-hexyl group on one side of our acetylene. Then we can take this intermediate and do the same thing on the other side. We can deprotonate. It's still a terminal alkyne because it still has the other side of the molecule. And so we can deprotonate that terminal alkyne to get an acetylide on the other side, react that with ethyl bromide to install the substituent on the other side. So we have to do this stepwise and we have to do it sequentially, because if we don't do it stepwise, then what happens is that we could form our acetylide anion. It would react with the hexyl bromide, and then it could, if we just dumped all these things in the same pot together, we could deprotonate the other side and it could add a second molecule of the same thing. That's why it's really important. First, we give it sodium amide, just enough so that every molecule is deprotonated once. And then we give it hexyl bromide so that all of those anions then get substituted with a hexyl group. Then we can go in a whole new sequence and in separate steps give sodium amide to get the acetylide and ethyl bromide to create our new carbon-carbon bond on the other side. So mechanistically, I went ahead and showed the mechanisms for the first step, where our sodium amide acts as a base to deprotonate acetylene to give us the acetylide anion, which I haven't drawn, but you can imagine, because it has a negative charge right here after you deprotonate. And that lone pair on that acetylene anion or acetylide acts as a nucleophile to attack the carbon that holds the bromine in an SN2 fashion to generate a new carbon-carbon bond right here and install that six-membered substituent group, giving us a total of 8 carbons now in our intermediate. And then in the second step, we add these last 2 carbons, and you guys can draw the arrows for yourself for the second steps as you're reviewing your slides later. Okay, so we've been talking about acetylide ions being nucleophilic and doing SN2 reactions. But the other thing that a good nucleophile could do is attack a carbonyl and do what's called an addition to carbonyls. So we already know from chapter 1 that it turns out that the carbon of a carbonyl is electrophilic. So the reason for that is because we know from chapter 1 that we can draw a resonance structure for this carbonyl. And just a reminder, carbonyl refers to a C double bond O. So we can draw the resonance structure for this carbonyl where we have a positive charge on the carbon and a negative charge on the oxygen and a single bond in between. And that means that the overall kind of hybrid structure for carbonyl is a C double bond O, but it has a delta positive on the carbon and a delta negative on the oxygen because of that other resonance structure. This makes this carbon an electrophilic carbon. And so our nucleophile can attack at the base of this carbonyl, or the carbon of this carbonyl. That'll generate a new carbon nucleophile bond, like so. And the pi electrons of our carbon-oxygen bond would have to go up to the oxygen and become a new lone pair in order to avoid breaking the octet rule and giving the carbon more electrons than it's allowed to have. So from here, now we've made one new bond and we've created an anion on the oxygen. Notice we've retained our formal charges all the way through. We had a negative overall charge on our combined set of reagents, and that negative charge is still in our alkoxide. From here, if we chuck in some water or a little bit of acidic water, we can protonate that alkoxide. And look what we've done. We have formed an alcohol. We formed a hydroxyl group out of this C double bond O, this carbonyl, and a nucleophile. So we have added our nucleophile across our double bond. All right, so what does that look like if we want to apply it to alkyne chemistry and the reactions of acetylides? Well, acetylide ions are nucleophilic, so they can do exactly this. And this turns out to be another very useful reaction for acetylide ions. So what does that look like? Here's a generic version. If we have our acetylide ion, which of course came from deprotonating a terminal acetylene using sodium amide. Once we have this acetylide ion, which is nucleophilic, it attacks at the base of this carbonyl, for example, any aldehyde or ketone. And the two groups attached to that carbon are just kind of spectators. They're just kind of along for the ride. So they're here still, but we're going to form a new carbon-carbon bond between the acetylide ion and our electrophilic carbon. And when we do that, we will take our pi electrons of our carbonyl and move them up to that oxygen to get this alkoxide intermediate. And then in a separate step, we can quench this alkoxide using water or acidic water, protonate that alkoxide to give us an alcohol or a hydroxyl group. So here's an example with real molecule, not just a generic version. If we had 3-methyl-butanone, which is a terminal alkyne, and we subject it to these conditions, we can substitute the other side of this double bond. And so here's what this looks like. In the first step, sodium amide will deprotonate our terminal alkyne to give us an acetylide ion. Remember, that looks just like a lone pair sitting on a carbon of a triple bond. That lone pair is strongly nucleophilic. And so if in our second step, we give it this molecule, which you guys hopefully remember from chapter 2, CHO is the shorthand for aldehydes. So this is an aldehyde group attached directly to a phenyl group. And hopefully you guys remember from previous slides that that phenyl group looks just like a benzene ring. So that's what this molecule looks like. Here's PHCHO, here's your benzene ring, that's the pH or the phenyl group. And then here's your aldehyde, CHO, the shorthand for an aldehyde. So when you have this phenylaldehyde, it's actually called benzaldehyde for this benzene ring. The acetylide that we generated in step 1, the carbanion we generated in step 1, can attack as a nucleophile at this electrophilic carbon that is highlighted with a green dot. And that will create a new carbon-carbon double bond between your acetylide and your electrophilic carbon. It will also create an alkoxide out of this oxygen atom, which you can quench in a third and separate step using H3O plus to generate the new oxygen hydrogen bond here and finish up our synthesis. So if you look at what we did, overall, we took a terminal alkyne and we substituted it on one side to get a new carbon-carbon bond and an alcohol group directly next to that triple bond. Here's another example. In this example, I'm showing you a ketone as the substrate, and I'm showing you acetylide anion as a reagent. Of course, we could have written it the other way with the acetylide over here and the ketone here. This is just kind of arbitrary what the substrate and what the reagent is, because they're coming together to form this molecule. So if we have a ketone, such as cyclohexanone here with this carbonyl, this carbon at the base of that carbonyl is electrophilic. And so if we have acetylide anion, which has already been generated for us, but if we needed to generate this, we could just use sodium amide and acetylene to get this sodium acetylide. And this acetylide can do nucleophilic chemistry, attacking at the base of this carbonyl to create the alkoxide of this oxygen. And then that would be protonated in the second step by H3O plus to give this product here, this 1-ethynyl cyclohexanol. Okay, on your own time, you don't have to turn this in. This is just for you. I encourage everybody to try to draw out the mechanistic steps of these two reactions. Actually draw those arrows for yourself. That is my strong recommendation. And then in the minute that I have left, I want to go over one more practice problem with you guys and have you guys thinking about how you would synthesize the following compound, starting with acetylene and any reagents that you would need. And actually, instead of going over this, I want to make one more comment about the last slide. If you look at our product here, our 1-ethynyl cyclohexanol, this is actually still a terminal acetylene because we brought in acetylene to start with. So we still have a terminal acetylene on the other side of that triple bond. This CH bond is still acidic, but now we've created a problem for ourselves because a hydroxyl group is more acidic than our terminal alkyne. So if we wanted to substitute on this side of the molecule, we would actually be in trouble because our base would not deprotonate here. Our base would deprotonate here at the most acidic site. So with that in mind, what I'm going to do is put up this practice problem, and I will post this practice problem on the slides, and I'm going to ask you guys to all think about this on your own before our next class. So what we need to do is come up starting with acetylene, the reagents that we would need to be able to synthesize this target molecule. And I want you to think about this, keeping in mind what we just talked about the acidity of this hydroxyl group. Because when we did our last practice problem, the order didn't matter. We could put on the right side first or the left side first. It didn't matter. But in this case, the order actually makes a big difference in the success of your overall synthesis. So go ahead and try that on your own before next class. You do not need to submit any of these. None of these are an in-class participation. They are just for you to try on your own. And on Friday, we'll start class by going over the answer to this practice problem. Any questions for me on this type of stuff? On Friday, we'll cover the other two kinds of reactions of acetylenes, the other two categories of reactions, the addition to that triple bond, which will mirror the addition to alkenes that you guys already know about, and the oxidation of that triple bond, which will mirror the oxidation reactions of alkenes that you guys already know about. I have office hours today from 3 to 4. I will be live in person in my office and available on the Zoom link. And keep an eye out on Canvas for announcements about other additional office hours this week so that I can help you guys stay on top of this material. And don't forget, you can always use the Campus Learning Center drop-in tutoring hours, which I always post on the last couple of slides when I post my slides. Thank you, and I'll see you guys on Friday.